Okay, so let's proceed with the lecture here. So this is an example of a MOSFET, okay, the N-channel E MOSFET. So if you get a MOSFET, for example, for this type of MOSFET, the 2N4351, okay, the 2N4351, so it gives you the schematic symbol here. Okay, the gate, the source, and the drain that you are familiar with. And then if we find the data sheet, it gives some information regarding the spec of the transistor. Okay, so we can see some of the specs here. But the important spec that we want to see is in fact remember that we want to find K. Okay, so if you remember that K is equals to ID on, okay, over VGS on minus VGSTH squared. Okay. Okay, so this K is a constant, and it depends on the process. It depends on the transistor itself. So where can we find ID on? Where can we find VGS on and VGSTH? So we can actually find from here. So the VGSTH is given there, which is 1 volt minimum, maximum 5. So normally we're going to use the minimum value here. The VDS, okay, we have a VDS on. Okay, VDS on, given that your ID is 2 milliamp and VGS has 10 volts. And then we also have our ID on. Okay, our ID on as 3 volts. Okay, so these parameters we can actually find from the data sheet, okay, of the transistor that we have. So from these values we can then calculate, okay, based on a certain configuration. We can then calculate what is our drain current and what is our operating point of the circuit setup that we have. Okay, so let's have a look here. So the spec sheet for the 3N171 lists the following values. So we have IDS at 10 milliamp, IDS on. We have so this occurs during VGS on at 10 volts and VGSTH is 1.5. So using these values that we have from the data sheet, we want to determine the ID for the circuit configuration that we have here. Okay, so the data sheet gives only the spec for 3N171. So if you have some resistors, okay, we have R1, R2, R1, R2, this will be R3, okay, RL. We have these resistors. So can we calculate what is our drain current and what is our VGS? Okay, what is our drain current, what is our VGS at the operating point? Okay, so the first step is to calculate K. So we have to remember this formula where K is IDS on over VGS on minus VGSTH squared. So here you just plug in the values, okay, 10 milliamps, 10 volt here, and then VGSTH. So if you do this calculation, we are going to get 130.4 microamps per voltage squared, okay, for our K. And our VS here is 0, okay, VS here is 0, is connected to ground. Therefore we can calculate VGS by finding VG, because VGS is VG minus VS. Okay, VG minus VS. So if VS is 0, VGS is actually VG. So how to find VG? So VG is right here. Okay, VG is right there. So how to find the voltage value at node G? Okay, so here we can see that actually it's simply a voltage divider where we have a 10 volt supply. Okay, we have a 10 volt supply coming in, and VG is in fact the voltage here. Okay, the voltage across R2. So the voltage across R2 is simply a voltage divider equation. So it's just VDD, which is 10 volts. Okay, VDD 10 volt. R2 over R1 plus R2. So it's just the voltage across. Since both are 1 mega ohms, both are 1 mega ohm. Therefore, we have a simple half of the VDD on VG. Okay, so your VGS is in fact your VGSQ. Okay, your operating point, different than this VGS. Okay, so VGSQ is 5 volts. So here is your VGSQ. So at the steady state, your VG is in fact 5 volt at that condition with the resistor and so on. Okay. What about your IDQ? Okay, so this is your IDQ. So your IDQ is given by this equation that we saw before. Okay, ID is K VGS minus VGSTH squared. So K is calculated already from here. VGS here is VGS on. Okay. So this is a VGSQ. Okay, this is a VGSQ that we calculate here, and here is your VGSTH that we get from here. Okay, so if we do this calculation correctly, we should get 1.696 milliamp as our IDQ. So what is IDQ? So IDQ is a current, okay, a current going across the transistor. Okay. So that's how we calculate for VG and ID. Okay, so some important concept to be aware of and to know is that your gate current is always 0 amps. Okay, so essentially we can say that is a infinite resistance on the gate. Okay, no current flows through the gate. Okay, so here IG equals to 0. Okay, so the current going through the gate is equals to 0. And then ID equals to IS. Okay, ID equals to IS means that this is your ID, so your drain current is equals to IS. So the current flowing through here is equals to current flowing through there, which is also equals to the current going through the transistor. Okay, so ID equals to IS. For E-type MOSFET, we have this very important equation, okay, which is just the equation that we saw before with the ID VGS curve. Okay, and the curve will depend on the value of K and your VGSTH. Okay, so let's look at this another simple example. So given this configuration where you have the RG, so here it's not so clear. So it's RG. This is your RD. Okay, this is your drain, your gate, and your source. Okay, so IG is 0. Okay, there is no current flowing through the gate, and therefore I here is equals to 0. Okay, so the current across RG will be 0 because your current through the gate is 0. Therefore, what is the voltage across RG? Okay, so V at RG is equals to 0 volt. Okay, it's given here. Okay, so VRG is 0 simply because your IG is 0. Okay, so if it's 0 volt, then we can simplify and just make a connection like this. Okay, so this one essentially is gone in our analysis. Physically it's there, but in our analysis we can ignore your RG because your IG is 0. Okay, so now we have a simplified circuit like this. So RD is still there, VDS, VGS, ID. So how to find your VDS and VGS? Okay, so we need to find and what is your ID? So you can see here that VG is equals to VD. Okay, VG is equals to VD. Okay, VG is equals to VD. Therefore, VGS is equals to VDS. Okay, so VDS equals to VGS. Now, if this is the condition, therefore we can actually calculate what is our VDS. So if you do the KVL loop, okay, all the way down, so we have VDD minus IDRD. Okay, VDD minus IDRD. Okay, going like this. Minus VDS is equals to 0. So VDS is equals to VDD minus IDRD. Okay, which is equals to VGS. Okay, so we have proven that VGS is VDS, and then we know that VDS is VDD minus IDRD. Therefore, we can we can get the operating points. Okay, the operating points for your drain current ID, your VGS, and also your VDS. Okay, so in this class, we are going to use a graphical method to find the operating points. Okay, so how to find the operating point? So here is your operating point. So the goal is to find what is the operating point for that particular circuit configuration given some resistors, capacitors, and so on. So here are the steps 1, 2, 3, 4 that you need to remember. First of all, we're going to plot the line using VGS equals to VDD at ID 0, and ID is VDD over RD at VGS equals to 0. So here is actually using the equation, the KVL loop. Okay, you're going to see later on an example. So here we're going to use a KVL loop equation, and then we're going to set VGS 0 and we're going to set ID 0 and find the other ones. Okay, besides that, we are going to okay, so this is a KVL loop. Okay, we have a KVL loop curve, and then we also have our the transfer curve. Okay, the transfer curve, we're going to use this equation. Okay, here is your K VGS minus VGS TH squared. Okay, so we have two equations with two unknowns basically, and we're going to intercept the two equations together to find our operating point Q. Okay, so where the line intersect between these two equations is going to be our Q point, and the Q point we can find the IDQ VGSQ, and then from IDQ we can also get your VDSQ. Okay, depending on the circuit configuration, using your IDQ or VGSQ, you can get your VDSQ. Okay, so using the value of ID at the Q point, solve for other variables in the biasing circuit. Okay, so let's look at this example here. So refer to the fixed bias amplifier circuit shown below. The MOSFET parameters are given. Okay, so K and VGSTH are given straight away. Okay, so remember K is obtained from the data sheet. So if you buy the transistor, they will tell you, they don't give you the K value. Okay, remember they give you the ID on value, VGS on, VGSTH, and you have to calculate K yourself. So so given the circuit configuration below, you want to find the operating point IDQ, VGSQ, and VDSQ. And the question is, can this circuit be used on an amplifier? Confirm that it's in the saturation region. So remember, it's in the saturation region if your VDS is greater than your VDSAT, okay, and VGS is greater than VGSTH. Okay, so this saturation condition. Okay, so in the end, our Q, okay, our Q has to be greater than that. So let's see. So let's see here. So if you have a circuit like this, okay, and we have a voltage, we have R1, we have RD, we have a transistor there with a given spec for this one. So you want to find ID. So where is the IDQ? So IDQ is the current going down here, your IDQ. Your VGSQ, okay, so here is your VG, your VD, your V source, okay. So your VGS, so here is your VS, okay. So your VGS is here, okay, VGS, and then here is your VDS, okay. The drain, the source, and the gate. Okay, so given this, we want to estimate or want to calculate what is our VG, what is our VS, and what is our VD. So VS is ground. Okay, VS is quite clear that your source is connected to ground, but the voltage on the gate and the drain is not so clear. Okay, and we have to make some analysis. Okay, so let's see how we can do this. So the first step is to remove all capacitors and draw the DC equivalent circuit. Okay, so what we did, so here is already without any capacitors. Okay, so these are the DC equivalent circuit, and the next step, step number 2, is to use this equation. So we've seen this equation already. 0.25 milli, VGS minus 3.5 squared. So remember, this one is your VGS TH, and this one is your K. Okay. And from here, we know that if I put my VGS 3.5, okay, so the curve looks something like this. Okay, so this is your curve. Okay, and we know that if your VGS is less than 3.5, your drain current will be 0. Okay, so therefore if you put in 3.5 here, okay, 3.5 minus 3.5 is 0, and therefore you have your drain current ID is equals to 0. Now what happens if you put 4.5? If you put 4.5, it's going to be 0.25. Okay, here is 0.25. I'm rounding to 0.3. If you put 5.5, it will be 0.25 times 4 will be 1, 2.34, and from here we have the values we need to plot this exponential chart, the line. Okay. So for example, 3.50, 4.5 is here. Okay, 4.5, and then 5.5 is there, and so on. Okay. So that's first step to get your exponential graph. The next step is step number 3. The loop line. Okay, here is your KVL line. Okay, your KVL line. So how to get your KVL line is just looking at your KVL line here. So 6 minus IGR1 minus VGS equals to 0. So how do we get that? So we can see here, if we look at this line, okay, okay, fine. Okay, so here is actually we're looking at this line. Okay, so 6 minus IG, okay, 6 minus IG R1 minus VGS is equals to 0. Okay, looking at the KVL, so it's a KVL, one KVL loop on the input, and IG equals to 0. Therefore, your 6 minus VGS is equals to 0. So your VGS equals to 6. Okay, so just a simple analysis there. So we have a nice and simple circuit here to test for our first example. So we find that our VGS is equals to 6. So that is our VGSQ. Okay, so that is our VGSQ. So here is our KVL, where here is your VGS is equals to 6. Okay, so VGS equals to 6 is our VGSQ. And what is our IDQ? So IDQ is the intercept between this line and our exponential line. And here we're going to get around 1.6 milliamp, and this is our IDQ. Okay, so essentially that circuit we can say is going to run ID equals to 1.6 milliamps and VGSQ equals to 6 volts. Now what about our VDSQ? So VDSQ, we need another loop. Okay, so we have another KVL loop here to calculate our VDSQ. So what is our loop going down? So our loop here is, so if you make here is 20 minus ID RD minus VDS is equals to 0. So your VDS is equals to 20 minus IDQ, VDSQ, okay, IDQ times 3.3K. IDQ is equals to 1.6 milliamps. VDSQ, okay, so you can just substitute 1.6 milliamp on the IDQ. Substitute there, and you should be able to get 1.7 14.7 volts. Okay, 14.7 volts for your VDSQ. Okay, and this is the final solution. So the final solution is VDSQ, VGSQ, and IDQ. So that's the final 3. So is it the saturation mode? We need to check our VDSQ. Is VDSQ greater than VD sat? So we need to check the spec sheet. So 14.7 is quite big, so it should be bigger than your VD sat. Okay, at VGS. Okay, so VD sat is VGS minus VT. So this is 6 minus 3.5 equals to 2.5. Okay, so we can see that our VDSQ is greater than VDSAT. Okay, so VDSQ is greater than VDSAT, therefore it's in the saturation. Therefore, circuit in saturation. Okay, in saturation, therefore we can make the signal voltage amplification. Okay, as that's our purpose. Okay, let's look at one more example here. Okay, let's look at one more example here. So it's quite similar. The only difference is that we are going to add the RS. And what is the effect of RS here in this case? So if you add RS here, then your KVL here will change, your KVL here will change. Okay, KVL2, let's call this KVL2, and here is your KVL1. Okay, what about your exponential equation should be the same. Okay, where your ID is equals to K VGS minus VGSTH squared. Okay, so this one should be the same as before. Your KVL1 is different than before. Your KVL2 is different because we have the RS. Okay, so what is our loop here? So KVL1. Okay, so for KVL1 is 6 minus IG R1. Okay, 6 minus IG R1 minus VGS minus IS RS equals to 0. Okay. Therefore, your VGS is equal to 6 minus, this is 0, because your IG is 0. Okay, so your VGS is 6 minus ISRS. Okay, or where IS equals to RD, so we can put ID. Okay, the current is all the same. So this is one equation. So this is called equation 1. This is equation 2. And equation number 3 is KVL2. Okay, and KVL2 is 20 minus IDRD minus VDS. Okay, remember this is your drain, this is your source, this is your gate. So 20 minus IDRD minus VDS minus IDRS is equals to 0. And therefore your VDS is 20 minus IDRD plus RS. Okay, and this is your equation 3. 1, 2, and 3. Okay, this is how you find your VDSQ and VGSQ later on, if you find the IDQ. Okay, so so we draw this graph, and we draw this graph from this loop, from the VGS loop. From there we get your IDQ, we get your VGSQ, and here is your IDQ. Okay, you replace your IDQ there. And you should get your VDSQ. Okay, so basically the same step as before. So let's have a look how they make here. So remove all capacitors and draw the DC equivalent. This one same as before. Okay, same as before. You can see this equation exactly the same. Now our loop is different. Let's see our KVL loop. So here we have the VGS 6 minus IDRS. Okay. And in this case, what we do is we're going to set 0. So if VGS is 0, okay, if VGS 0, what is the value of our ID? Okay, RS is given. Okay, RS is given. RS is given, so we can calculate the ID is 8.8 milliamps. And then when ID is 0, okay, so you make this 0. So easily we can see that VGS equals to 6 volt. Okay, so now we have these two values. We have one value and another value, and this value we are going to put 6 at 8.8. Okay, there might be an error here. This should be okay. So when VGS is 0, okay, so when VGS is 0, okay, when VGS is 0, we want to have okay, we want to have an 8.8 milliampere. Okay, we want to have 8.8 milliampere on this load line. Okay, so this is your load line KVL. Okay, so you have to be careful. I think there is an error there. So 8.8. Okay, VGS6 at ID 0. So you can see the ID 0. So ID is 0. We're going to set our VGS equals to 6. We have the first line, we have this line, and the intercept is just going to be your IDQ there and your VGSQ, which is going to be 5.5. Okay, so this looks correct. Okay, that's around 5.5. And then here also looks correct, is a 0.7. Okay, so from the graph, we get the IDQ, we get the VGSQ, and then we're going to take this value and put it inside there. Okay, I'm going to put the value inside there. And how we get this loop, we already seen in the previous slide. So 20 minus IDRD minus VDS minus IDRS equals to 0. Then we can calculate our VDSQ is equals to 17.2 volts. Okay, so just simply like that. So just a recap on the step. So we have 3 loops. Okay, we have we have 3 equations. Sorry, we have 3 equations with 2 loops. So the first equation is the exponential equation, which is this graph. Okay, and the gate to source loop is a load line. Okay, this gate to source loop is a load line. Get the IDQ, get the VGSQ, and from the IDQ we take this is the drain source loop. Substitute the ID with IDQ, and you should get our VDSQ. Okay, so that's just a summary here. Just a summary. What is the use of the source resistor RS? Okay, so this is the source resistor RS. In the previous example, we didn't have the RS, and now for this example, we have the resistor RS, and what it's for is the source resistor RS helps to stabilize the Q point. Okay, by having this load line. Okay, if you don't have RS, you're gonna have a straight load line, and it's not going to be stable. Okay, it's not going to be stable as the one with RS. So if the gate bias increase, the source current will increase, but not as much as when there is no source resistance. Okay, so this is a key point here. This will later affect the AC gain. Okay, later we do some AC analysis. We should have, or we must have, a source resistor. If not, we're going to have an impact on the AC gain. Okay, therefore the source resistance is necessary to stabilize the Q point. Okay, so that's it for this part of the lecture, and we'll continue in the next video for the next part.